Good afternoon. So today we will discuss about electron microscope. So last class little bit we discuss about optical microscope and basics of why requirement of basic microscope and why the electron microscope is required. So today we will mainly discuss the two microscopic technique. One is scanning electron microscopy and transmission electron microscopy. So this we have already discussed. Being electron has more shorter wavelength than the visible light, this allows electron microscopes to produce higher resolution image than standard light microscope. And electron have the strongest interaction with matter of any radiation. So many type of information will be available to get, and it is because of high intensity, high energy beams of electron, it's quite easy to generate because of thermonic emission electron, and it is used in conjugation with various techniques like it can use during immunolabeling, negative staining, thin sectioning, all those type of different type of study can also be possible by using this microscopic electron microscope. And the electron microscope that use wavelength in the range of 0.002 to 0.1 nanometer depending upon the energy of the electron. So you have a wide range of possibilities to scan of different size that you can able to see. So this is the basics of electron that we have discussed. When electron beam incident on a material, it interact with a particular electron volume, and there is possibilities of generate of secondary electron, and the secondary electron as well as secondary electron as well as backscatter electron. So that too used in scanning electron microscope, and the electron that transmitted through it, so that will be used in transmission electron microscope. So these two techniques, in addition to that, there are other possibilities are there, X-ray generation or J electron generation or cathodoluminescence. But we will mainly focus on scanning electron microscope that use backscatter electrons and secondary electrons. And second thing, that is transmission electron microscope that use transmitted electrons. So coming into the scanning electron microscope or SEM, if you see, the SEM is a type of electron microscope that produce image of a sample by scanning on the surface of the focused beam. Like you have a surface here, on that surface the electron microscope that it will scan, like a raster scanner is there, so that raster scanner will scan on the surface, and then it will give the pixel by pixel that will get the images, and that will be constructed to form the final image. So electron interacts with the atom in the samples, producing various signals that contains information. If you see the history, you can see the right side that this first SEM built by Knoll in German, and then Jones in USA 1940s. You can see this is such a big scanning electron microscope at the initial stage. It becomes practical reality by Professor Sir Charles Otwell Lab at Cambridge in 1950. And then the concept of now it's mature, but progress is unabated. So still more and more development is going on this microscopic techniques. So if you see this, a scanning electron microscope mainly gives four information. First is topography, morphology, then composition, and crystallographic information. So if you see the topographic, this is the SEM image of barium titanate. You can see here how the intergranular fractures are there. Here you can see the different fracture surface. So those information, like mainly surface features of an object, how it looks or its texture, relation to these fractures and material characteristics. So mainly topographic surface information you will able to get by using SEM, and also shape and size of the particle as in relation to these features and material characterization. Like the morphology can also be obtained by using scanning electron microscope. You can also find out composition, that's elements or compounds that present in the material and its relationship between the composition and how it's related to the material characteristic. All those parameters you can get. In addition, you can also get from diffraction that pattern. You can also able to get crystallographic atoms arrangements of the object, that relationship between this arrangement. Like if you see the 3D structure or something, how inside that you can go to high resolution FESEM field emission SEM, they are able to see the atomic arrangement is possible. So topography, morphology, composition, and crystallographic information you will be able to get by using this scanning electron microscope. And if you see that scanning electron microscope, the magnification is in the range of 15x to 2 lakh x can go up to, and resolution is about 50 angstrom, and it is excellent depth of focus. Like you can easily that focus the underneath and you get the information from underneath layer. Relatively easy sample preparation. That SEM sample preparation is very easy as compared to transmission electron microscope. You can see at 10 kV to 100 kV, mostly it uses 30 kV in SEM operates at 30 kV per wavelength is about order of 0.02 angstrom. So for sample preparation, we see a conducting sample, so you have no need of any special preparation. You just attach to that, you have a sample stage that is there. On that you can directly, your conducting sample, you can directly by using double-sided black tape or some, you can put there, or in your putting in a brass top, you can disperse in solution somewhere, evaporating solvent like highly evaporating solvent like acetone or something, then you drop cast on your substrate and it mount into the stage. You're able to see that. So attached to the mounting stop for insertion in the instrument, and it may need, if conducting pathway. So if you have a sample here on the stage, you're putting sample, and the sample to the stage, you have to provide a conducting pathway by using silver paint. If there is no conducting pathway, what will happen? Your electron can be accumulated there. So because then the charging effect will take place. Because of the charging effect, you will see white, the material become broad, or say a white background there. So that will interfere. So you have to provide a conducting pathway. If it is non-conducting, then you have to coat it with a thin layer of either this AU carbon or chromium coating, and then you can use it for the some sample studies. And this you can put in the sample stage, but then analyze to get the image. So sample stage can be tilted. So depending upon the specimen size, so you can tilt the sample to get the fracture morphology, cross section. All those things can be possible. If you go for the even this non-conducting sample, that can be used in a special case of the environmental SEM, ESEM, that called ESEM. So there you need not to provide conductive coating, where there it operated a very low kV in nitrogen argon atmosphere. So there you can also use non-conducting materials. But mostly for non-conducting material, you have to coat a thin layer of chromium, carbon, or copper, or gold. If you see the comparison between optical microscope and the scanning electron microscope, you can see the optical microscope, just you are able to see the grain boundary here. So even that is not looking fine properly. So but if you go to that barium titanate, this is the optical image and this is the SEM image. If you see in the SEM image, you can able to see the growth steps, how this this structure is growing. So those information you can able to get, and you can see here radio Olarian is the optical microscope SEM. You can see that the spikes, all those spikes is clearly visible in case of SEM, and internal morphology here is not clear, but here you are able to see very clearly. So comparison to optical microscope SEM, you have magnification is very high, 500 kx, whereas only optical you have only 1400 kx, 500,000 kx. In case of SEM, your depth of field is much higher and resolution is also quite good. So SEM has a large depth of field, which allows the large amount of sample to be focused at one time and produce of that image with good three-dimensional characteristic can be seen here, and it can be combination with higher magnification, large depth field, and greater resolution. You can able to see the compositional crystallography information, or you can able to find out there. So if you need the optical microscope, you have a small depth and low resolution, but in SEM you have a large depth of field and high resolution you can achieve using optical microscope. So how does it scan? So if you see that in case of SEM, the beam scan the specimen in a raster manner, like you have a object here. On the object you have a scanner, So that scanner will scan on the surface like this. It will scan, and then that it will go to the collector, and finally it will reach to the image. So image will produce here in the similar manner. So you have a synchronous raster is there. So that helps in the scanning the top surface. So signal produced as a beam spot is placed at each position, in turn is collected and used to control the brightness of the display beam, which writes the image on the screen. So it scan here by pixel, and then it transfer it to the scanning stage, that the image is here. From the scanning stage to image, there again it write that particular structure. So you will be able to see that image by pixel. It's most like if you see the 3D Century mosaic structure, you can see in this image there are small rectangle squares are there. So all those you can see as a pixel, they will scan in each individual squares, and finally it will reconstitute the image in the image plate. Okay. So here if you see the instrumentation part, on the top of the surface you have an electron source that is mostly used as a tungsten or barium hexaferrite, lanthanum, lab6 lanthanum hexa, this L hexa boride lab6, that is one, and tungsten. Those things are nowadays even FEG, SEM, their field emission gun, they are used as a source. And then from the source, it's processed to different anodes. Here, that magnetic lenses here, where the electron acceleration takes place, and finally it comes to the sample surface through different aperture as well as objective lens. So it will form here. So once it falls here, you have a backscatter electrons or secondary electron. Both is possible. The backscatter electron will come back here. The detector is placed here. The backscatter detector that will detect that one and produce image. The secondary electron, you have a side detector kept here, so that the secondary detector, mostly silicon, lithium, SiLi or semiconductor detector that use here, and you have a EDAX there, that EDAX analysis that can be possible by using that. What are the X-ray produced here? So that X-ray can able to get the composition analysis. So mainly that you have a backscatter and secondary electron that to produce. So that is the low energy that backscatter is used for the topographic contrast, whereas the backscatter electron, which is a high energy compositional contrast, you will be able to using the backscatter, and you have X-ray that will be used for composition analysis. So brightness of the region in the image increases as the atomic number increases. Like the Z value increases, the brightness will be more and more pronounced. So you have a less penetration gives more backscatter. Z value increases, so that will happen. The penetration that this will be harder, so that the optic density of the material will be higher. The penetration depth will be decreases. So you have in case of that, you have a backscatter electron will be is less penetration, gives more backscatter you will be able to get. So if you see the electron beam source, so you can see different type of what happened, that electron, the top that this if you see this samples electron source, so that is kept in a high this there the thermonic emission takes place here, high potential thermonic emission takes place here by electric current. Once the thermonic emission takes place, the thermonic source rely on the heat generation of the electron. So once that this field emission source, that also called FEG gone, that are strong electrostatic potential, like you have a high electrostatic potential on there, you have a tungsten or an FEG source is there, and from there because of thermonic emission, electrons will be generated. You can see for this is a tungsten filament. Then this is a lab6 lanthanum boride. You can see a tip type of structure, or is there the tungsten tip, both can be used in case of the field emission source. So from this, the SEM requires high current density, that is electron for unit time per unit area, high current density, and small electron spot is possible. So that means that your tip or the filament should be it's so soft, so it can be generate more the thermonic emission is possible, and electron that high current you require to produce better electron emissions. So if you see the electron gun, that one mostly tungsten and the lab-6, as I told, and filament had negative potential, it's high negative potential it has to cap, and walnuts produce the small negative bias. You can see here, you have an anode here, that electron beam will be produced here from this walnut cylinder here, the electron is produced, and then that electron beam through various magnetic lenses will come through the sample surface. So if it's tungsten wire, it is a wire type thing, or in case of lab-6, you can see how tip type of structure. So tip of the tungsten needle is made up of very sharp, that R is less than radius less than 0.1 micron. So if it is very sharp, then you are able to easily resolve, very good resolve the images, and you can obtain, very good pictorial image of your samples. So nowadays, instead of this using this, to earlier we mostly use this tungsten wire and lab-6 that are used as a source, but nowadays we are also using the field emission gun. The strong electric field is used. Initially it's harmonic emission, now it's field emission can also be possible. It's now in modern edge microscope, mostly FESC, FPGA, that uses this electric field is used. And you can see here that this is the source from where that electrons are generated. You have first anode and you have a second anode V2. So this is the electron anode is there, acceleration anode, and this. So first electron extraction voltage is here. The electron first electrode, they will extract that one. Second electron arctage electrostatic lens, and different extraction voltage for different mode is possible. You can see here for tungsten you have a beta that is 10 to the power 9 order brightness if you see, and lab-6 is 5 into 9, where Schottky and cold FEG can see is much higher. That means your Delhi NR is 0.3, so you can able to see the structure of of the order of this type 2.5 nanometer. And you see all these things you need vacuum from 10 to the minus 3 to 10 to the minus 8 order. So you can see the how sharp is a tip of this FPGA guns. So a smaller spot and higher current density compared to harmonic emission. So you are able to go high resolution because of a very small spot can be possible here, and high current density compared to electronic harmonic emission. So if you see the image quality, all of those things, it will depend upon the wavelength of the huge scanning electron microscope. So that huge and effect on the applied voltage strongly affect it, and also role of vacuum. So if it's a resolution increased as the wavelength decreases, and in similar penetration depth will increase, specimen damage, that may be side effect, and image contrast also decreases by varying the voltage. And vacuum, you need all those samples has to be kept in high vacuum in the FPGAs, 10 to the minus 10 or minus 6 in case of lab-6, and the chemical corrosion thermal stability is necessary for well functioning of the filament or gun pressure. Because of that you need a high vacuum situation in case of ACM. Then the vacuum requirement is dependent on the type of the detector, what type of detector we are using. So that depends. So it is a common normal lens where 1 by u plus 1 by v equal to 1 by f. This is the object distance, this is the image distance, and the focal distance here. But similar type of thing occur in case of SEM, where by instead of normal lens, you have a magnetic lens kept here. So schematic cross section of a magnetic lens and light analogous of the convex glass. You see this is the convex glass like that. It's a electronic. This magnetic lens is that huge to focus the field. You can see here if you go into the optics of the SEM, you can see for conventional image you will see a large size, but it's opposite. It's an inverse image. Okay, so scanning electron microscope is light passing through the origin here. This orifice here, you will get the display image. Similar, not inverted. The same site you is able to see by using a scanning electron microscope. And the scanning electron microscope, as I told, it uses two types of electron. One is backscatter electron and another is secondary electron. Because of that, so mostly in case of backscatter electron, it's a solid state detector. So that you can see the sample is here and detector is here. So just behind that, the backscatter electron is coming back, it will be detected by this detector. So detector site is just above the sample. And images are more sensitive to chemical composition, electron yields depends on atomic number. They have a higher Z atomic number, so that will produce penetration will be low, so backside electron probability is much higher. But another detector is secondary electron detector that mostly PMT or scintillator detector uses here. So that here is needed in front of bias mass is there. You can see the electron beam falling here and it's migrating in an angular path, and then detector is here to collect that information. You see, if you see the magnification thing that in the cunning electron microscope, that magnification LCRT, what they see in the screen by L specimen, the magnification is controlled by two parameters. The magnification is accompanied by scanning a progressively smaller portion of the specimen and displaying the image on CRT screens. That you can see here, that here the image is here, but here that change in magnification at constant y. The walking distance, the sample to sample, this is sample and this is the position of the electron that stage that where it's falling on the sample. So that if you vary this walking distance, so you can see here change in magnification at constant, though without changing walking distance, the magnification was enhanced. You can see the same image, how this to this, you can see how enlarged, then this, and then you are getting more better information about the array. But in case of walking distance, if you change, what should happen? At constant magnification, you will able to get better image, but position of that image will be changed from that particular area. You can see here, this is the image that you are seeing. So here in the image on a CRT, it will be enhanced, it will be increased, and you will get a magnification is controlled by changing strength of the scanning coil. So if your scanning coil change, that the magnification will be changed. You will be able to see image on CRT, large image of the CRT. So as I told, by varying the depth of the by from the sample to this sample to source, that the distance of the tip of the electron beam where is coming, so that you can able to get that depth of field that you can get by changing the walking distance. You can see here the focal plane is here, but here you can change the focal plane by varying the walking distance. So depth of the field, that the DOF, is the distance along the potential optical axis either side of the focus point that remains in acceptable range. You can see here by varying the walking distance, top at 8 mm, 8 mm, and below at 30 mm, 30 mm walking distance, 8 mm walking distance, 100 micrometer aperture, and 37 mm walking distance. You can able to see the quality of the image, how the image quality has been changed. This is the height over which the sample can be clearly focused. That you have a particular height, so be above that, the sample will be particularly properly come closer or go far away, your image will be brought, you will not get a better quality image. So SCM has a large depth of profile which produce the image that appears in a 3D structure. So depth of profile, depth of field is depends upon the longer working distance, smaller objective aperture, and lower magnification. By varying these parameters, you'll able to see the better quality image in this case. But if you see, this is a coil, that image, scanning electron microscopy image is focused at the square here, and will still be focused at large magnification. Like a charging effect has nullified the coating with carbon. So you can see here this white thing. If there is any charging, those things can be overcome by silk carbon or gold coating. And then you can see, if you magnify this, then you can see here, initially you have this type of structure. You are not getting any internal morphology, but slightly go to 10x to 110x. So you are seeing the internal morphology here. So if you go to further 200x, you can see the inside force and how this structure is, this pattern looks like. And then if you further go, you can see the microchannels here inside this in 400x. And if you further go, you can see how clearly they're visible with all the force channel, and at much higher at 16,000 K or something, you can see how the birds growth in the this structure. So those information in module 45K, we're able to see a most clear image of this particular board you will be able to see here. So that means by changing the magnification, you can get the more and more information with better quality images. But if you see that both, as I told, scanning electron microscope that use both secondary electron as well as backscatter electrons. If you see that the second electron also, which is a cracked structure on the surface of the insect hair, this is insect hair, on that the cracked surface is here. But this cracked surface is not visible properly here. But if you see here in the second, that is the backscatter electron, as I told, backscatter is good for topographic images. You can see that better structural information than backscatter. But in case of imaging, if you see that is the only backscatter, is backscatter first plus secondary electron, both simultaneously. If you are image using these two, then you can see they're still getting a better clarity images. So backscatter electrons are mainly high energy, and then the brightness of the region image increases as the atomic number increases. The secondary electrons are low energy, that is used for topographic constant high resolution images. Secondary electron, that is that in addition to that, which produce fluorescent X-rays, that is used for compositional analysis. Mainly that SEM will give you information about the topographic image, surface morphology, then all those other things that elemental composition, all those parameters can be possible to get. So if you see that, as I told, that it's possible to identify the chemical composition or identify the constituent present in the material by using energy dispersive spectroscopy, redox analysis. So during this process of generation of secondary electron, so once you have a core electron, so that knockout, then that secondary electron, that coming out from this here, that during the process of generation of the electron, so once electron is coming out from this surface, so what will happen? There will be vacant site will be created by producing the X-ray photon or fluorescence. So outer cell, when it will, like you have a, you can see here, you have an electron here, and that electron knockout. So what will happen? You are now you have a hole here. So on that hole, some other electron, like from X-ray, they will come and occupy that. And during this, one outer cell electron fills the inner cell electron and producing X-ray. By the time X-ray will be released, so that X-ray is called, X-ray fluorescence. And each element has finite X-ray signals, like different element is there, the corresponding K alpha or K beta, different energy. So energy dispersive spectroscopy based on energy of X-rays that can be possible, and determine amount of element present, like up to 0.1% accuracy can able to measure. And you can full point, line, and C-scan are mainly, all scan analysis are possible, that you can go for a, like this is the composition, you can see here that this is a silica sample on that this is silica presence or iron presence. You can see all this EDS spectrum of mineral crust. You can see how these phosphorus, calcium, iron, they are distributed here. And then with a 0.1 weight atom percent accuracy up to, you can see, and then you can see this is a element of Jadeno sample with a spectral scanning of manganese. This is a cobalt sample with cobalt scanning. You can see how the manganese are distributed into this whole image. So cobalt is distributed, those things can be possible by using redox analysis. So if you see, as I told, there is another one, that is the environmental scanning electron microscope that is used to overcome some of the shortfalls of the scanning electron microscope, especially for insulating sample it's used, and vacuum sensitive of the sample, biological samples, those things, irradiation, sensitive sample like some thin organic films, so that once you irradiate with the laser beam, also or some electronic beam, so there is some damage or those things will create. So to avoid those things, biological sample or some like oily sample, greasy sample, most those information like bacteria or virus you want to see the surface morphology, you can use the scanning electron microscopy. It is also used to image, chemical and physical process in situ, like mechanical stress, oxidation state of material hydrogenation or dehydration, all those things can be possible if you have also use the image of chemical physical process in situ, some other equipment you attach, you'll be able to see all those information. You can see 10 to the power minus 6 the pressure is there, so there you have to use that scanning electron microscopy to study the surface morphology. So especially if you see the scanning electron microscopy mainly gives the information about that four things. One is topographic information, one is shape and size, that morphology, and then you'll able to get crystal information. So all those information as well as composition analysis, whether what type of particular element present, how much it constitutes atom percent, what percent, all those information you'll able to get by using scanning electron microscope. For scanning electron microscope, you need your sample preparation is not that difficult. You simply take a chunk of material and put on the carbon tape and mount on the sample holder, or you have a liquid sample, you disperse them with some solvent like acetone, and then you drop cast it on a substrate, silicon substrate or brass substrate, and finally put it on the stage for analysis. But for conducting sample, you can directly use them, but for non-conducting sample, you have to make them conducting by using some sort of carbon, copper, or this chromium or gold, the carbon, chromium, and gold coating on that surface, and then you can use them for analysis. And in case of environmental SEM, you're able to see the biological samples where with much lower vacuum you can able to operate in case of scanning electron microscope. And that scanning electron microscope on the top surface of a raster scanner, and that scanner will use that scanner by collect the data by pixel, and it will be some added up, then again in another in the screen, and you're able to get a 3D or something reconstituted image. So this is about that mostly scanning electron microscope. So we will discuss that another one, that is transmission electron microscope, that is mainly useful for shape, size, how to see the materials, that is about nano range, like about less than 10 nanometer or so, or you can see 5 to 100 nanometer, able to see all the shape, size, or morphology, and you can able to get electron diffraction pattern. So there you can identify the phase font. So here we will take 2-3 minute break, and then we'll discuss about transmission electron microscope. So now we will start transmission electron microscope. It's in case of scanning electron microscope, there was a raster scanner. So that raster scanner, it scanned on the top surface by pixel. But in case of transmission electron microscope, the electron beam has to transmit it through the sample. A sample has to be less than 90 angstrom or so. So it can transmit it to that this sample substrate sample, and then you have a charge detector at the bottom or a photographic film on the bottom where you can get a image. So if you see here the historical background of transmission electron microscope, so this TM, that is a unique tool to characterize crystal structure, microstructure simultaneously by diffraction and imaging. But in case of SEM, there is only imaging was there, and then from the imaging there you are using secondary electron and basic electron to get information about the topographic or subsurface morphology, or the compositional information. But here you are using in case both imaging and diffraction, both is possible in case of transmission electron microscope. So it was discovered by Knoll and Roscoe first at 1931, which was about 400x magnification only. So later on, it was subsequently, the image that the electron microscope, the transmission microscope was slowly developed more and more advanced version, and Simon developed his first commercial TM in 1939, and then all modern electron microscope are now mostly the Rosca prototype. The resolution you see from 400x to now 2 million times has been enhanced. Even at 100 kV, you have a wavelength that is about 0.0039 nanometer that we utilize. So the wavelength is so small, what will happen, you'll able to get much more information, like more efficiently the small image of atom diameter about 0.3 angstrom that can be resolved here. You can see the 100 keV, your resolution is 0.24 nanometer. When UV light, if you say 365 UV light, your resolution is 159 nanometer. See how advanced is your transmission electron microscope to get better resolution structure. And then nowadays the microscope are coming with imperfection free lenses, free, that is largely that those are corrected spherical aberration, chromatic aberration corrected. The microscopes are now available that to overcome the limitation, this lens imperfection limitation. And Knoll and Rosca, Rosca got this Nobel Prize in 1986 for the discovery of transmission electron microscope. If you see that this beam is about less than 100, that thickness is less than 100 nanometer, not angstrom, it's in nanometer region. So your electron beam can be transmitted through this, and then once the transmitted, so one will be directed beam here, and then you have an elastic scattered beam and an elastic scattered beam. So from using this transmitted beam, so for the direct or elastically scattered beam, the direct beam or the elastic scattered beam, they are used to produce image with contrast due to the mass thickness, depending upon the thickness of the material, whether this much thickness or this much thickness. If you have this much thick and this small thick, so if you have penetration transmission, it will less here, light here, your transmission is much easier. So depending upon that mass contrast, the Z value difference or mass contrast thickness value, so you'll able to see the better image as a diffraction effect, and it produce diffraction pattern effect to see the crystal structure. And then during this time you have a that what is a inelastic scattered electron beam is coming here, that these two are used for imaging, and the inelastic what is coming here that loses energy here, that inelastic scattering. So during this, for the electrons, incident electron and transmission electron energy is different. So there what will happen, that will use to get that electron energy loss spectroscopy, whatever energy is lose here with interaction with the material, so that will produce a electron energy loss spectroscopy, will able to get chemical information. And what are the X-ray produced during this time, characteristic X-ray, so that X-ray you can use for mapping, or you can spectrum, you can get for compositional information, elemental information you will able to get from the EDAX analysis also. If you see that schematic outline of a transmitted electron microscope, it is an electron source like SEM, the electron source here, that source is again tungsten or lab 6 you can use here, and then after coming from this, here electron will be generated, and then it will pass through different lenses to attenuate that acceleration, to attain that high acceleration, high speed, and then it passes to the condenser aperture, condenser lens here, it will go to the objective aperture, objective lens with the aperture, and finally it will fall through the sample, and then the sample it will go to the projector lens and the fluorescence screen. So you're able to get the the image here, or either you have a film here, or your fluorescence screen, or you have a CCD charge coupled detector that will be able to get the direct image. So if you see that the schematic here, you have a condenser, many condenser lens here, magnetic lenses they are made up of, then your objective lens here, you have a sample here, and after sample it will go to the intermediate lenses, and finally it will fall in the through passing through the projector lens, it fall in the fluorescent screen or camera chamber that kept just below here. But in case of the detector, the EDAX detector, which lies somewhere here this side, so that the electron beam scatter, so the X-ray is producing from there, that will be used for EDAX analysis by using this TM EDAX. So this T imaging and diffraction, as I told, that two things is possible in case of transmission electron microscope. You see what is the basic difference in case of imaging and this. In case here, if you see that the electron gons in both cases it is there, then electron beam is produced from electron gun and it will passes through the condenser lenses here. Then it go to the specimen. In both cases, you have a specimen. After specimen, the electron beam will be transmitted, and then it will be objective lenses, and through the aperture objective here, it will passes through a the different lenses to create the image. You can see here this of the image plane of the object plane, the selected area aperture that you can see that here the back focal of the objective lens, the objective lens is kept here. Here the objective lens, in image plane, this is the plane of the image. So there it is that objective lens is kept close to the image plane. But whereas in case of the intermediate, let's see, here it is in between of the sample and the image planes. This is back focal plane, it is kept there. So mainly the intermediate lenses that use here, that the strength between the two regimes. So here that the lenses are used, that lenses they are of different strengths. So you'll get in case of here what is happening, that the same electron beam is falling to the created image, then it is going through the projector lens to produce a diffraction pattern. So difference between the two mode is only with the strength of the intermediate lens. So whatever the lenses are kept here, so that the intermediate lens that is of different strength. Here you can see that this is focusing at the here that back focal plane of the objective lens, where the image plane it is focused here. So that because of that you will able to get you have an imaging mode and you have a diffraction mode. In an imaging mode, diffraction mode, you have diffraction in the aperture that has to be selected aperture, you have to insert it here. So this is the selected aperture here. But in case of this, which is in a back focal plane that you are keeping here, the selected aperture, what will happen? So you can see on the selected aperture that the focus point is here in this case, but here it is on the intermediate lens that is falling here, selected here. So basic difference in between imaging and diffraction will be the strength of the intermediate lenses that used here. From the electron microscope, the microscope that is this time TM that produce diffraction pattern. You can see here that electron beam is coming here, and you have a lattice plane like this, and after here it is transmitted it's slightly diffracted here. You can see in this case. But because of this, depending upon the plane, you have a lattice plane 1, red one, and green one, lattice plane 2. So different spot you will able to get on the this film. So you can see if a single crystal, this type of dotted plane you will able to see. So diffraction of electron beam is schematically deficient. The crystal the line present a set of parallel lines. And here the diffraction pattern generated by diffraction of electron beam. You can two parallel lattice plane is there. One is red and green. You can see depending upon the particular what are the electron beam is oriented to the particular lattice plane. When it is oriented to the green plane, you will be able to see this green dots. When it is red plane, you will see the red dots. So you are able to see this type of electron patterns. Electron diffraction pattern. So you have a polycrystalline structure. That means you have a many grains are there, many grains are there. So that means different planes, each possibilities exist there. So for each, like for example, 100, if I see 100 plane, so that 100 plane will be available in case of this red crystal, and that may be available in some other UN also. So that because of that, so you'll get many dots you will be able to get, and these all dots they can be fused together to form a ring type of pattern. This is a pattern of a Fe3O4 nanoparticle. You can see these different dots, they come closer to form a this type of ring structure, and then you can analyze those rings to find out the each plane from this. That we'll discuss. And if you see the electron diffraction pattern, if you amorphous material, you will able to see the amorphous, there is more long range ordering, you will able to see this type of highly diffused ring. But if you have take a single crystal, you can in a single crystal, they're mostly ordered. The electron beam passing through the single crystal produce a pattern of spot. If a single crystal is only one plane is oriented here, you can see, so you will able to see only dots corresponding to that particular plane. But in a polycrystalline, there are many planes are there. So made up of tiny, single crystal. Many they like you can see this is one single crystal. So different orientation. So many crystalline materials are there, polygrains are there. So what will happen? So all those dots you are getting here, like they will merge, like this dot you will be able to get on the ring. So they will merge to produce a diffraction pattern. Looks like superposition of many single crystal spots and resulting in a concentric ring you will be able to get in case of polycrystalline material. And crystal structure and lattice parameter can be obtained from this electron diffraction pattern. If you see the phase identification and detection, identified characterization that you will see now, and then you can able to see here. You can see here. You can draw a UL sphere. If you see that, as you know, in the reciprocal lattice, in diffraction pattern, but when that particular point lies on this Oswald sphere surface, you will able to see that plane. So here the 1 by lambda is the diameter, and you see the lambda of that X-ray diffraction pattern and electron diffraction is much different. So X-ray it was 1.54 angstrom in case of this copper K alpha, but here in this case of electron diffraction at TM, the wavelength is about 0.0025 nanometer. So it is very, very low. And because of this, here 1 by lambda is much bigger. So what will happen? The Oswald spheres look like it's a big hemispherical type of structure, a big sphere where that almost that surface will look like a flat. So that means more number of diffraction spots fall on this ring, on this UL sphere. So what will happen? You will be able to see much more information than corresponding to X-ray diffraction pattern. But the thing is, the only problem is electron diffraction pattern analysis. It's much more difficult. That's why it's not that much user friendly as compared to the X-ray diffraction pattern. So if you see here, you can see that sine theta. You can write here lambda equal to 2d sine theta by equation like the sine theta is lambda by 2d, and you have a this lambda equal to 2d sine theta, and theta is, you can see here 2 theta, that is very, very small here. That diffraction, if you, as I told here, this you can see here the diffraction 2 theta is diffracting at a very, very low angle. Because of that low angle diffraction, that sine theta you can take is at a theta, so it will be lambda equal to 2d theta. So this angle is very, very low. You know, sine theta, that will be this R by L will be sine theta. This is sine theta formula. It will take sine theta equal to R by L, and that R by L equal to, in theta is very very small, that is equal to 2 theta. So considering these two, equation 1 and equation 2, you will get RD equal to lambda L, where R equal to this ring, whatever the ring you are getting on the photographic film, that this ring radius, that will be your R, ring radius will be R, and D equal to D spacing. If your crystal structure like sample here, and that D line spacing, that D spacing is D, diffraction spacing, and lambda equal to wavelength, that is constant, that you are using 0.0025 nanometer in case of 200 keV electron microscope, and L is your camera length, that is constant for each spacing. You are keeping fixed by imaging, so that you will able to get. So only unknown parameter equal to D. By using this equation, you can easily able to get the D spacing, and then you can compare the corresponding D spacing which you are getting with that of the X-ray diffraction pattern. You can see here, this I have identified this F3 220 plane, 311, 400. All those different planes can be calculated by simply using L lambda RD equal to L lambda, that you only know parameter D that can be calculated if you remember measure this ring diameter. So it's difficult to measure the ring diameter. What you do, take a instead of ring radius, you take a diameter and then half of it that radius are. So nowadays that this whole equation is that instrument used to taken care. So in case of providing this image in reciprocal, in that is equation here, that instead of nanometer it is coming 1 upon nanometer unit. If it is 1 upon nanometer, that means that L lambda is everything is taken care by this software. So what you just measure the distance and then calculate R value 1, you have a radius R, you go for 1 by R, that R inverse, that radius inverse, ring radius inverse, that you will get, D spacing. You directly get in the current used nowadays available scanning is the TM microscope. So you can see here simple cubic 1 by D square equal to A square plus K square by A square by A square. So you can able to whatever the Miller indices is possible, you can identify in FCC, BCC, all those things you can able to identify by using this, diffraction rings. But if you have a spot pattern, like a single crystal structure, you can see here, these are the spot pattern. So there you have a G1, G2 are the distance you measure here, and this distance will be G1 plus G2 summation of this. 2 will get this. Like you can see the 0, plane here, and 0, 2, 0, and 1, 1, 0 plane. If you identify here, then this will be 1, then the 1, this 0 plus 1, 0, 1 equal to 1, and minus 1 and 2 will be 3, and this 0, 0. So 1, 3, 0 plane will be this. So accordingly that you can calculate it, measure the distance of the diffracted spot from the center spot. Once you identify the center spot, you measure the distance, then this distance corresponds to the D spacing of the reflecting planes. From the reflecting planes, that distance you can able to find out, and then the angle between the drawn line of the central spot, the diffracted spot, and you can measure. If you know the index for the closest set of diffraction spot, it's possible to index. If you know these two, you find out, then this you can calculate, and so on. You can keep on every diffraction spots can be reached by a combination of these two vectors. So these two vector combination, this, and then accordingly if you go on, you'll be able to identify the whole ring pattern. In addition to that, if you have an amorphous structure, that we used to get a diffuse ring, and the diffuse ring can be radial distribution function can be find out. Radial distribution function, you can use the intensity, how the intensity is varying across these rings. So you can get a intensity distribution, and then you calculate the radial distribution versus length R. So you'll be able to get this type of fit from there. So you can be recorded and measured, and that will be useful to give you, instead of distance between neighboring atom, it follows a probability function here. So the probability of how the intensity is decreasing. So you can able to get information from the amorphous material, those short range ordering, all those things can be get. A new technique like fluctuation microscope. So that also medium range ordering you have, you can able to use this fluctuation microscopy, how the radial distribution function is varies, and you can able to get information about amorphous materials. So if you see the TM imaging is almost similar to that of scanning electron microscope. Only difference is there. Here you don't have a raster scanner. Instead, that electron beam is transmitting. You can see the electron gone at the top surface, and then it is transmitted through the sample here, and the different objective lenses are there. And the objective aperture, just that I told, is in between these two in back focal plane, and finally it comes to the screen. So the image of the specimen is formed selectively, allowing only transmitted bright field image. So there is a possibility of two types of beam that is transmitted. Like one thing is bright field, or a diffracted beam that is called dark field. So if you see here, so bright field and dark field image first we will discuss. So you can see here that you have a sample here. From the sample, the electron beam is falling here. So after transmitting, if an electron beam is transmitting, this is directly it's going like this, these solid lines, and then it's fallen through the aperture, objective aperture. It passes through and create a image here. That is a bright field. With the direct beam, the image is produced by the direct beam here. What is the direct beam transmitting? So that will give you the bright field image. You can see here this objective aperture that is just lies at the center here. So image formed from the direct beam you look here. But if you have a indirect beam, so what will happen? That is that you can see this is a dark field image that produced instead of direct beam, we are using a diffracted beam. So instead you fall on the sample here, then it diffracted an angle 2 theta. So here it is diffracted. If that beam, if that beam is passing through this aperture, wherever the direct beam is getting stopped here. In previous case, if you see that here the direct beam was transmitting here, diffracted beam was stopped here by the objective aperture that was producing bright field image. But if the diffracted beam is going through, it's producing image that we called a bright field image. You can see this is the two different positions that you are doing. Objective aperture is mainly preventing the direct beam. So one or more diffracted electron beams that allow to pass to the objective aperture to get this dark field image. So that means this you will able to get that both dark field and bright fields, and the origin of the image contrast with the variation of the intensity of transmission beam or the diffracted beam due to the difference in the diffraction condition depending upon the microstructural feature. That means if you have a sample here, if it depends the diffractional condition of this or how the direct beam is transmitting on depending upon that. If the image is thick, that is the mass contrast or the thickness contrast is the main thing that will produce the contrast difference in TM image. Like you have a big the thick sample or the high density sample, penetration of electron beam will be less. So what will happen because of that? And then you have a thin sample or less jet sample, the electron beam is much higher, transmutation is much higher. So what will happen there? It will be that it will be less darker. Whereas so thick sample, the image will produce more darker. That means you have a possibility of mass thickness contrast. That contrast appears in the image due to the difference between inherent scattering of the sample, like you have a thick sample or a thin sample. Depending upon that, your mass thickness will be different, and also there is a Z constant depending upon the Z value that transmission beam that intensity will be. Then you have a diffraction contrast. In crystalline material, the diffraction mainly occurs utilizing the objective aperture and either the direct beam, one or the selected area that you can see here that you have a. If you go to the diffraction pattern here, you can see that depending upon this particular data, how the objective aperture that you are putting here. So instead of putting that this here as a center, so here as I told, instead of putting here the opposite aperture, if you varying the strength of the intermediate lens, if the objective aperture put somewhere here instead of here, we bring it to here, you'll able to get that diffraction pattern. So that So you will able to get that diffraction constant. So result in crystallographic information by conveying the by being conveyed in the image, or the diffraction you will produce the direct diffraction used to get crystallographic information. And then you have a high resolution image that is a phase contrast, and that use both directed beam and in diffracted beam both. Like instead of using that, you have a sample here, as I told you that this is the direct beam that is going on. This image you are using in bright field, and you have a this beam is getting diffracted, and that beam is passing through. Then we are getting here dark field. But in case of high resolution image, so both diffracted and direct beam both are used, and then we have interference between these two phases. These two will take place, and we'll get better high resolution image by using that phase contrast microscope. So if you see here that as I told, this direct field that is directly goes to the sample here, but if you indirect the dark field image that we are producing, the diffracted beam you can see here, this is the direct beam. So this is the direct beam that should go, but you can see instead of using that, the direct beam is coming here, they are getting stopped by a aperture here, and to whatever the indirect beam, diffracted beam is coming here, so that beam is going to the sample, the aperture to form a image. If this beam is direct beam is diffracting, and then you are using, it's a it's called dirty dark field image. But this is because dirty dark field means that here this has to be the focus position, but that there you are preventing that the direct beam, and you are getting somewhere here. So but if you center dark image, so here instead of that in the top that light which falling on the perpendicular to the sample surface, instead of that you make in an inclined electron beam, so that is falling here, then let it be diffracted in an angle 2 theta, which will be the diffraction is now perpendicular. You can see here passing on the perpendicular to the aperture, to the lenses, and then going to the aperture at the center position here. So on axis dark field, that you can say this is off axis dark field that will produce a dark field, and dirty dark field, and center dark field that will be using on axis dark field will get a better image. You can see here how the mass thickness can vary your image of this TM. You can see this is low Z material this side, and this side you have a high Z material. You can see in low Z your electron beam is transmitting much higher. You can getting a opposite type that image here. But in case of high Z material, you can see the electron beam transmission here will be less. So particularly the image transmit, this is thickness is high here, so with that high Z here, that you can see the transmission is less here. You are getting this image less transmission beam, and here it is high. The low, this is this thickness is less, so you're getting this type of image. Similarly, in opposite side. So depending upon the thickness as well as low Z variation, you can able to see the image in the mass in the TM. But when you have a Z, is almost like is quite different. You can see this is a silica coated Fe3O4 with the silica coating. Then the center dark one is Fe3O4, and outside this is this less darker area is SiO2. So the outside is SiO2, and inside is Fe3O4 is here, because the silicon and the Fe, that their case Z is that Z, if you see Z in these two, is much difference is there. So because of that atomic number different, the Z contrast, you can see that the darker, that high Z, the transmission is less, you are getting darker, whereas in the top surface, outer side, the silica, your transmission is high, you are getting a core cell structure. So you can identify the core cell morphology by using this type of, the mass contrast TM imaging. This is an amount of zinc oxide sample that use that I told bright field and dark field information. You can see this is taken by bright field. You can see the sample is mostly grayish color or dark. You're seeing this is also a bright field image, but here the bottom one is taken the center dark field image. You can see, so the white spots, those are mainly the grain structure that is there, the crystalline grains they are able to see. In this case of a dark field image, it looks like a white, the sample looks white here, but in case of grace, the bright field sample become gray or dark black here. So, so this is the image quality you can get different information, but this is the amorphous nature, and that how the crystalline the dots those are available mean because the particles those the information can able to get by using this bright field dark field image. So in addition to that TM you have a scanning TM, that is scanning transmission electron microscope is possible, and you can able here in the like in SCM here STM has a raster scan. So that raster scan will help you to get the you can see here the morphology in case of TM, the internal information you are missing here, so the topographic information. So those information inside you can get here because of this scanning tunneling electron microscope. And here mostly we use a high angular detector, dark field detector here, so that to detect that all this information to the raster scan. So better contrast image, better image contrast can be achievable by STEM, and more forgiving the sample thickness even though it's higher, so you can able to get a better quality image, and low beam damage is possible. And here both EDAX and yields analysis, like you can chemical composition, like simple chemical composition you can able to get by using STM. So this is a STM image of cobalt after zinc oxide. You can see here this is the STM image, and then by scanning that spectral mapping you can see the different copper, zinc. The copper is mainly this is cobalt is there. Copper is mainly due to that copper substrate that you use as a this copper grids, and cobalt you can see cobalt and zinc that you are getting from this sample. And then you can go a line scan across if you have a sample here, and then you do a line scan, and then from the line scan, like for example cobalt I'm doping on this zinc oxide matrix. If my cobalt is uniformly distributed in the structure, like one side to other side, if you go like this electron beam, so this is a thick area, and this is spherical on the top surface. What will happen? You will have a much higher interaction time with the slowly. Here top to go to center, what will happen? More number of copper you will able to get here because of the this interaction with this electron beam. So what will happen? And then we go to outside again, that cobalt composition will decrease. So in between the cobalt will be there. So if it's uniform distribution, what will happen? It will keep initially it will increase here to start, and then it will keep on increasing. The center will be much higher, then again it will decrease. That means it will give a hemispherical type structure. This type of hemisphere that indicate that the hemispherical spectral mapping, mapping will show you uniform distribution of your dopant. Those things one can't find out. And also you can do the copper K alpha imaging. You can see here, this is a zinc K alpha, and that's K alpha mapping, not copper K alpha, it's only K alpha mapping of that constituent element. This is iron K alpha. You can see here that this red signal is from zinc and this is iron, and how you can see that this is hemispherical way copper is distributing. Zinc is there, but in case of iron, it's random distribution. You can see here iron is higher, here is less. So those information we're able to get. So that means this is a porous structure, network structure in that small nanoparticle aggregate to form this zinc oxide, Fe3O4 zinc oxide composite. How Fe3O4 is distributed in this and for this porous network, that information you can able to find out. And but if you have as I told, if you have a different Z, then you have because of Z contrast different or thickness difference, when able to see the core cell structure. But if you have a equivalent, almost similar Z molecule, similar Z component, like if you take this two example I have shown here, one is PD and PT, one is nickel cobalt. You can see PD and PT, their Z value is almost similar. Similarly, nickel and cobalt, their Z is almost same. So being same, it's very difficult to see in mass contrast thickness. TM mass contrast, by mass contrast, it's very difficult to see this core cell information. For that, you go for this STM imaging analysis. You can see you image analyze here is for PD and here it is for PT. Then you superimpose these two, you will get this type of how this red and green dot both are distributed, and those information whether it is core cell or is uniformly distributed. Here you can see these are more randomly distributed inside that. So those information you can able to get this. You can see mostly that this inside that PD, if you see here, they are mainly segregated inside and green dots are outside. So that PDPT core cell structure can be identified. And similarly, you can see this alloy formation. Initially, cobalt and nickel, they were like this core cell structure, outside cobalt, inside nickel. Then you apply heat treatment. Once you heat treatment, take 440, 550, and 600, you can see here the nickel instead of core cell is started distributing, and finally nickel cobalt alloy formed. So this green and red also are pushed to get an yellow is completely they are overlapping, mixed with each other. You can see from electron diffraction, electron mapping, you can see here it's a core cell type structure inside and outside. You are seeing the red dots, but once you go to 600, it's converted to green and red mixed to form the yellowish color. So by that way, you can able to in situ elemental mapping is possible by having similar Z material, so that can be identified by using STM mode. So as I told, so the electron beam which is transmitting through the sample surface, the two types, one is elastic, one is inelastic transmission electron beam. So if it is inelastic, so that generally used for this dark field, bright field imaging. But if it is elastic, if it is inelastic, so there will be some energy loss. So whatever the energy loss, so that energy is used to determine the chemical composition. So that uses the electron energy loss spectroscopy or seal spectroscopy. That in inelastic scattering, that energy is reduced. Like if the electron is less than the E0 is initial incident E0, the transmitted electron has energy less than that of E0. So this loss of energy is measured by yield spectroscopy, and it has three regions. Like you will get this type of spectra. In that spectra, there will be three regions. One will be zero loss energy. You can see here, this is zero loss energy. That means there is mostly that you will get a elastic zone, and then is a low distribution and core loss, low loss distribution and core loss region. Low loss distribution about 100 electron, from 0 to 100 electron. Here there will be low loss, like mostly plasmonic peak or low loss distribution are able to see. That electron that have interacted very weakly with bound electron, like they're not they're not elastic, but they're interacting in an elastic manner, but the interaction is very low. So because of that, you will get a low loss distribution. And then there is a core loss region for electrons that have interacted very tightly bound core electron. Like you have an incident beam, your system, your sample that has a core electron and is a valence electron, they are outside. So the outside valence electron are loosely bound. If those incoming electron being interact with the loosely bound electron, so their interaction is less, you will get loose bound electron, get sample thickness here mainly about 100 electron volt. If that once it interact the core electron, the interaction will be much high. So you get it because of that tightly bound. So here beyond 100, so that will got core loss region. So that will be used to calculate illness, that energy loss near Earth spectroscopy, like X-ness in case of X-ray, absorption spectroscopy that I discussed. So here illness that will provide you oxidation state of the material, and you have a like X-jabs in X-ray absorption spectroscopy, you will get X-labs, that extended energy loss fine structure, X-labs. So that provide information about the coordination number or atomic distances, like symmetry, coordination. Those information you can also get by using yield spectroscopy of TM, transmission microscope. So that yield spectra, you can also get this type of spectrum, yield spectra. So you can identify how the oxidation state titanium +4 or +3 is there. Those information you can get. You can also get backscattered image, like we combine like TM, like SEM. You can also get this type of TM, transmission electron microscope, the EFTM, that image you can get, and you can STM EL spectra. You can see how that in this structure titania is here, and then this aluminum and oxygen. It's a titanium aluminum overlay. So titanium, aluminum, and oxygen. You can see how this layer structure outside it is about oxygen. Then you have aluminum. Then you have a titanium red one. You can see layer structure by using this yield spectra. So the last part of this of today's talk will be on high resolution transmission electron microscope. As I told that high resolution that phase contrasted transmission electron microscope that mostly use both direct and indirect that diffracted beams. So those two transmitted beam and diffracted beam, they will interfere with each other because of their interference. If they are in this coherent scattering is possible, the transmitted and diffracted beam where each other have a different phase. Because of that interference pattern, you will got a high resolution image. That phase contrast image will get by combining both transmitted as well as the diffracted as well as direct beam. So you can see here your objective aperture is quite big here. So that means here you can see this is the direct beam and this is the diffracted beam. It's coming here. So diffracted beam both the sample surface on the top after sample is direct and this is the diffracted. So both are considering and you have a very large objective aperture. And that aperture, because of the large aperture, you will get much more information like atomic resolution thing you can able to see. So image is found by interference of the diffracted beam and fringe contrast made up of bright field, dark field. When you have a one phase is there, then the coherent scattering will be possible, or let's say interference, coherent interference. That constructive interference, I can say constructive interference will takes place and will get better information about the atomic plane. You will see the dark lattice that will be like this plane. You will see the dark portion will be the atomic plane. You will be able to see. Depends upon the operating condition. You can able to say thickness, or if it's properly focused, you will be able to see the the thickness and focus are the two parameter where it depends that you have to properly focus, and otherwise what will happen if it's properly not defocused, then you will not it's not properly focused, and this just will not you'll not able to see those things. You can see here this is the lattice plane that you can see here. These lines are lattice plane. Then you can measure the distance between these planes either by using this scale, or you can use by this. You can create a Fourier transform and then FFT image. Then FFT. So from this image you get this is a FFT Fourier transform image, and then from FFT you go for IFFT. This will be you can generate this type of I inverse Fourier transform that will be itself. So before going that, what will happen? You just you profile mapping you do across this line, so you'll get this type of peaks like this. Then you measure the distance between two peaks. You'll able to get that interplanar distance. So that interplanar distance will match it to the particular plane which is oriented to the electron beam. So in addition, you can also create a FFT Fourier transform, and you can able to get this type of soft pattern. You can say like from a particular crystal you can get. And then if you have three thing here, many crystals are there, 1, 2, and 3 crystals. So you can interface information you can able to get. Like you create a Fourier transform, then you inverse Fourier transform, you will get IFFT. What will happen? It will background correction it will do, and you can able to see those atoms here. So you can able to see how these atoms are distributed. If you go to high resolution, even directly you can able to see this atomic information. You can see here this 1, 2, 3 grains are here. They joined, fused together to form a bigger one. So you can see here that after IFFT, if I get the Fourier transform, inverse Fourier transform, I get this image. You can see how clarity is this image, and then here you can see one plane is coming here, then it bifurcated like this. So here is a beam, they bifurcated like this. So those type of defect dislocation you can able to find out. You can see this plane is going like this plane is going like this. So here is a plane, so that is bifurcated here. So those dislocation that you call line dislocation, those information you can able to get from HRTM imaging. If you further go high resolution, you can able to see these atoms, how this in zinc oxide and nickel doped zinc oxide, you can see how the atoms are hexagonally this is a hexagonal closed structure, how they are hexagonally, arranged in this. If you see here the proper hexagon, you can see here. Yeah, this is the proper hexagonal distribution of the atoms you can able to see, and then you can see if you go for a better inverse Fourier transform, you can see how the waves natures are there because of the stacking fault, the dislocation. In addition to dislocation, there is some slightly displacement of atom, how it's happening instead of going straight. So this bend is here. So those thing information you can see here. So the plane is coming here. This plane should be arranged like this, but later on it's deviate from the main line to position atoms are go arranged like this. So there is a deviation. This deviation is called stacking fault. So those metallurgical information we are able to see. So similar to TM, if a biological sample, so they will burn out because of high keV use, that 200, 300 kilo electron volt used in transmission electron microscope. Those biological sample or organic sample, they can burn out. For that, we have to use cryo-TM, that is cryo transmission electron microscope, that operated at very, very low temperature. Either you have to feed the sample in liquid lithium, liquid methane, and then you go for imaging using liquid nitrogen, all those type of free structure. Then you can see there's a cryo-electron micrograph of a liposome. On the liposome nanoparticle, you can see the liposome structure is the double layer structure. You can see here 2 layer is visible here. And if you have a cryo-TM of micelles, you can see how these micelles, the micelles are nothing but surfactant molecules. They self-assemble to form this. Micelles is a microscope, a giant marine virus. You can this virus structure you can freeze. So structural, that biological information you can be able to get this agency to operate. The cryo-TM operates at 220 K electron volt. It's much less than the 200 used in TM. So here that can huge. You can detect the biological information. So there are some drawbacks of the lens, that aberrations are there, lens aberration are there, that will interfere to the imaging quality. So you have a spherical aberration, that instead of or you have a aperture diffraction, chromatic, there is multiple focusing point is here. You have a eye astigmatism, is there focusing point 1 is here on the central beam, and transient plane here is meeting. So those type of defects that in lenses will interfere in your sample image quality. But nowadays most of these aberrations are corrected microscopes are now available. So for sample preparation, this is quite difficult in case of TM. Then in case of SEL. So in case of TM, if you have a metallurgical sample like that, you have a bulk sample like steel or something, then you cut into small pieces, then mechanical lapping, ultrasonic, you have to cut a very, very small thickness. Then what will happen, you have to do, this manual lapping, that you have to keep on cross section, and iron milling, you have to mill the top surface, remove the top layer, and finally you'll get a very, very thin cross section, section. So that you will go for, after iron milling, will go for imaging analysis, like a 250 nanometer thick. You are reaching a iron mill, you will few 100 nanometer or so, then you'll able to see that those type of information. In case of metallurgical sample that I have shown here, you can see that you have this bulk sample, then you cut it like this, and then after this you further cross section one particular grid like TM grid like thing you take out, and then this one you can see here in this surface, you can see how this less than 100 micrometer here is less than 10 micrometer, small, very small thickness you're able to get. So that will be used for TM analysis to see the phase separated or the carbide formation in the metallographic sample. So those things you can see. But if you have a nanoparticle, that you can simply disperse in a suitable solvent. So best solvent is ethanol, that you can disperse there. You can also use water, but ethanol, if you go to water, that evaporation will take little longer time. So during achieving vacuum will be take more time. But if you take ethanol, that you upon putting on after dispersing the sample, you make quantity of sample to minimize as much as possible so that you will get a translucent solution, and then after 20 to 25 minute dispersion, you put a drop on the sample surface, the TM grid, and then you take that, you dry that grid on the UV light and go for the sampling by analysis by using TM. So your dispersion is very important parameter for the nanoparticles to not be concentrated enough so that instead of getting, you will get agglomerated particles. If a biological sample, you can make them different cross sections like using staining agent, negative staining, soft micelles, vesicle. You can go for different steps for staining, and what will happen? You will be able to get back by in the bacteria or something, whatever the particles, or in the cell, that inside the cell, that morphology, or how the nanoparticles are distributed inside the cell. You can often by initially you have to mount it that the cell inside this epoxy or resin, epoxy or acrylic resin. Then you make a cross section, ultramicrotomy. You get a fine cross section and you put on the TM slide. You see those internal informations. So in addition to SEM and TM, that other microscopy that used widely for getting information on nanoparticle is atomic force microscopy, that using that mainly this contact by tip. You have a tip that will scan on the surface, either contact mode or tapping mode. So you will able to get that atomic force microscopy, AFM, and then you have a electrostatic force microscopy, magnetic force microscopy, or scanning tunneling microscopy that can use for nanoparticle characterization. So those part I'm not going to discuss. So I discussed today mainly two techniques, that is scanning electron microscope and transmission electron microscope. So these two microscope that used for imaging of your sample. So you have that SEM that will use for topographic imaging, and mainly I discussed the two techniques that SEM will be used for. SEM will use for topography, surface morphology, composition analysis, or even crystallographic information. For a biological sample, you have to go for ESEM analysis, environmental SEM. But in case of TM, that you can get information about atomic resolution and elemental mapping, that is possible. You can able to get identification of individual element. You can get oxidation state, bonding information by using yields facility. You can get the crystal structure information by diffraction pattern. So whether it's a polycrystalline, single crystal, you can identify there, or you can get defects, dislocation, stacking fault. Those things you can analyze by using this high resolution TM, grain size, grain bond information, as well as by for biological samples. You can use the cryo-TM to see the internal features. Maybe we can use also scanning tunneling electron microscope to get the tomographic information, this core cell structure, all those things can able to get by using TM. So main important thing for the TM is sample preparation. If you prepare your sample very good quality, properly, then you will able to get better. So if there is any question, you can put in the chat box, or you can mail me, and we will discuss the next class. So if there is no question, then we will discuss the next class, that will be on Monday. So we'll mainly on surface characterization technique, that's X-ray photoelectron spectroscopy and Auger electron spectroscopy, and secondary ion mass spectroscopy.